Alright guys, so here I am chilling in the Shenzhen airport and just thinking, hey, I should do some physics. So why not? I'm going to do some physics. We're going to go through your quiz. And this way you'll be able to check it right after you take it. Isn't that great? Alright, so I'm going to do my best to just kind of go through each of the questions that we got. And hopefully this will make sense. I'll try to give you where IB will give you the points and all that kind of stuff as well. Alright, so here we go. Question number 1, the electric field strength between two oppositely charged parallel plates. What is the answer? Well, for this, really make sure that you remember you draw the field plates. Remember we had one that was positive, and then we had one that was negative, right? That was the plates. Remember, it goes from positive to negative. There's your field right there. And it's all the same, except, remember on the edges, it's going to go out a little bit. Now, what does that mean? That means on the edges, it's a little bit weaker, because remember, the distance between the field lines shows you how strong the field is. So, because on the outside here, it's a little bit farther apart, that means the field is weaker. So, which of the answers represents that? The answer is letter D. Smaller at the edges than in the center. In the center, it's definitely stronger than on the edges. All right, next question. Which of the following gives the resistances of an ideal ammeter and ideal voltmeter? Now, this is what we talked about last class. Remember, we were talking about the ammeter. In order to measure the current, remember, ammeter measures current. In order to measure current, I need to make sure that all the current is flowing through my ammeter. So in order for that to happen, I need to make sure that the ammeter has 0 resistance. So it can't be this one, and it can't be that one, because the ammeter has to have 0 resistance so that all the current flows through there. Now, once I have that, I look at the ideal voltmeter. And remember, the voltmeter has to be connected in parallel, and we want to make sure that none of the current flows through it, because when the current flows through the voltmeter, it messes up the resistances of the whole circuit and all of that. And so the voltmeter, we want to have infinite resistance. So the answer here should be B. I'm starting to get some strange looks, some people getting up from their chairs as they decide that they are bio folk and they don't want to listen to physics. Well, go for it, dude. All right, next up, we got a metal wire X with length L and radius R has a resistance R. A wire Y of length 4L made from the same material as X has the same resistance R. What is the radius of Y? Okay, I'm not going to do all the work for you here. Hey, this is you. You're supposed to be doing some stuff, but there is a formula, remember, that relates the resistivity and the resistance, right? And then there's a bunch of other stuff here. I'm going to let you go find it in your packet because I want you to get used to what you're looking for there. So remember, that's going to depend on things like the length and the area and, of course, your resistance here. Okay, so the resistance is not changing. It's the same metal, same material. It says right there, so it's the same material, which means the resistivity is going to be the same. So the length is going to change, and the area is going to change. Remember, area, it's the cross-sectional area of your wire. So if we're looking at the radius of the wire right there, then area is pi r squared. And so use that in this relationship. Make the length 4 times as big. What does the radius have to be in order for the resistance to stay the same? All right, so that's the question that you're looking at there. You should end up getting letter A, 2R here. All right, okay, moving on. Those, of course, are 1 point each. Moving on to the next question. 3 identical filament lamps, X, Y, and Z, are connected as shown to a battery of negligible internal resistance. The filament lamp X breaks. Which of the following correctly describes the change in brightness of lamp Y and lamp Z? All right, so we're going to go ahead and look at this. We've got current initially is flowing here. It splits up and goes through both Y and X, and then it comes back together to go through Z and then to the end. Now, what's going to happen when X breaks? Okay, When X breaks, you no longer have this parallel situation. Now remember, when it's parallel, your resistance goes down because you have a choice of where the current's going to go. It's either going to go this way or this way. And because the current can choose which way it goes, you actually have less resistance in the circuit. Now in the circuit, V equals IR. I'm looking at the whole circuit here. So if I have parallel, the resistance is going to go down. And if the resistance of my circuit goes down, but the batteries stay the same, the cells stay the same, what's going to happen to the current? In order for the potential to stay the same of the battery, that means the current is going to have to go up. So I'm going to have higher current when I have less resistance. Okay? So when I had X, I actually had more current flowing. Now, yes, it's going to split, but I'm actually going to have more current flowing through the Z here. So when X burns out, that means that I no longer have this lower resistance. My resistance is going to go up. That means the total current has to go down. So if the total current goes down, what's going to happen to Z? Well, Z should get dimmer because the current's going down now. And so it's got to be either C or D. So we're taking out A and B here. Now what's going to happen to Y? Well, the current used to be splitting to go through X and Y. But the current no longer needs to split. It's all going to go through Y, which means Y is actually going to get more current. And so therefore lamp Y needs to increase. And my answer is C. Awesome. Moving along. Next question. Which of the following is the correct way of connecting an ammeter and connecting a voltmeter in a circuit designed to measure the characteristics of a thermistor? Well, you may or may not know what a thermistor is yet. Don't worry, it really doesn't matter. The question is asking about the voltmeter and the ammeter, right? We talked about the ammeter needs to be in series. The ammeter has to be in series because you want all the current to flow through it. If it's not in series, then not all the current's going to go through, and you're not going to actually measure the current that you're trying to measure. So therefore, it can't be B or D. The voltmeter, remember, is going to have infinite resistance, which means it needs to be in parallel. If your voltmeter is in series and you have infinite resistance, then all the potential difference is going to be across the voltmeter. It's going to take away all of that power, and so therefore the thermistor isn't going to get any current at all. And so therefore the answer has to be the ammeter in series and the voltmeter in parallel. You can go back and double check your notes. I'm pretty sure I said the same thing last class. Moving on. Coulomb's law refers to electric charges that are, and the answer here is point charges. Remember, we had to assume that all of the charge is in the middle. We talked about this when you guys did that silly little lab where you were checking the two, you had the two atoms or molecules or whatever it was, and you could adjust the distance and the charge and that kind of stuff, and you're exploring Coulomb's law initially. Well, that we assumed that all the charge was in the middle. That's the distance that we were measuring, and so that's really the key, is that we have to assume that both of them are point charges. Otherwise, the charges here and the charges there are going to be closer than the charges here and the charges there. So to simplify, we just say, you know what, all the charge is at the center, and therefore it's going to have just this one single distance, and I don't have to worry about different distances and all that other fun jazz. All right. Awesome. Moving along. We're doing good. We've got 3 positive charges here with equal magnitude at X, Y, and Z. So each of these are positive. Which of the arrows show the electric field at P? Remember, the electric field shows what would happen to a positive test charge if you placed it there. Well, if I put a positive charge here, it would receive a force from X pushing it away. It would receive an equal force because it says it's at the midpoint of XY. So an equal force from Y pushing in that way. So those two are actually going to balance. And now it's going to receive another force from Z pushing straight away, right? Because again, all of those are positive. It says they're 3 positive point charges. And so the answer after A and C cancel out is left only with B. All right, this last one should be pretty straightforward. Which diagram best represents electric field? You should remember that the electric field inside of a sphere is nothing, so it can't be either of these two. Remember, we said the electric field inside of a sphere, whether it's solid or hollow, it doesn't matter, but the electric field is 0, so it's got to be one of the other two. And now we are talking about electric field So the electric field due to a negative sphere is what would happen to a positive. Well, a positive would go straight towards that negative sphere. So your answer must be answer C. All right. That then gets us through all of our multiple choice. Woo, yeah, doggy. We are moving on. We're going to move on and we're going to start talking about some of these free response here. The first one is worth 1 point. Define the electrical resistance of a component. This is basically word for word from your notes. This is the potential difference across the component divided by the current through the component. Okay, and you do have to say across the component and through the component. If you just say potential difference divided by current, you do not get this point. It has to say through the current. Through the component and across the component. Okay, that's an important part of this. So make sure that you've done that. All right. Number 2, explain whether or not the filament obeys Ohm's law. So I'm not going to write everything here. You should be able to look at the graph and recognize, first we should say, well, Ohm's law says that potential difference and current are proportional, right? So that potential difference is proportional to current. So that should be your first statement, is to say, well, Ohm's law says this. Potential difference is proportional to current at constant temperature. Remember, that was important, so at constant temperature. And then the second point is to say, but this graph does not show that they're proportional because it's not a straight line. And so because Ohm's law says they're proportional and this line does not show proportional, therefore it is not Ohm's law. Okay? If all you said was Ohm's law is not obeyed, you get 0 points. 1 point is for talking about Ohm's law and defining what that is. The second point is explaining why that is not valid. And you have to do both of those to get the points. All right? Okay, next part. Calculate the resistance of the filament lamp when the potential difference across it is 2.8 volts. All right, so what I'm going to do is I'm going to go to the 2.8 here, and I'm going to measure it up to the line here, bloop, 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 which is about there. And I'm going to see what the current is at that point in time. So it looks like it's about 0.33, 0.34. In reality, they're going to give you credit for anything between 0.32 and 0.34. Okay, when I look at it, if I wasn't using my fat pen on my iPad here, I'd probably say it's a little bit less than 0.34. I'd go for 0.33 or 0.335 or something, but either one of those should work just fine. And so once you have your current and once you have the potential difference, which is 2.8, then you should be able to do V equals IR, and you should be able to solve for the resistance. Okay, so your first point here is for getting the current and saying that the current is somewhere between 0.32 and 0.34. The second point is for getting the correct resistance, which should be 8.5 ohms. All right, I'm going to trust that you can plug that into your calculator once you get the equation and everything set up. Okay, next II is, now I'm competing with the public announcement here. She can just move over because physics is more important than whatever she got to say right now. So we are moving along, II. And so this one should be simply using that equation. Again, it's the one I mentioned before, the one that has resistance and resistivity and area and length. You find that equation. You should be able to put in the length. You should be able to put in the resistivity. And we already know the resistance. We found it up here. So if you put all of those numbers into the formula, you should be able to get the cross-sectional area as being 2.7 times 10 to the negative 8th. So that would be your area. Once you get the area, of course, you do area equals pi r squared, and you should be able to solve for r. The next point is 9.3 times 10 to the negative 5th. So you get 1 point for substituting numbers into the correct formula. You get 1 point for getting the area and 1 point for getting the final radius, which is 9.3 times 10 to the negative 5th, and this is in meters. All right. Moving on to the next question. 2 identical filament lamps are connected in series with a cell of 6 volts and negligible internal resistance. Using the graph on page 26, that's actually the graph that was up above, calculate the total power dissipated in the circuit. So each lamp, if it has a cell of 6 volts and 2 lamps, that means that each lamp should have a potential difference of 3 volts, right? Because they're in series, so 1 volt will lose 3 volts, and then the other one will lose 3 volts. And so you should end up then with a 3 volts per lamp. You can look up 3 volts in the graph up there, and you should be able to get the current. Once you get the current, then you should be able to calculate the power. And so your total power should be about 2.1 watts, okay? If you did the 6 volts instead of the 3 volts, then you may have gotten 3.1. If you got 3.1 watts, that's probably what you did. You used the 6 instead of the 3, and in that case, you can give yourself 1 point instead of 2. All right, I'm gonna have to finish this later because my flight is boarding.